Hi guys, this is the EdExcel AS Level Further Maths Paper 2 covering the Further Statistics 1 FS1 module, and it's from the June 2019 series. Okay, so examiner report wise, what we see over here mentioned is that the candidates were well prepared for this paper, which proved to be accessible to almost all. Some of the explanations lacked a little of the detail and rigour required by the new specification, but overall the quality of work seen was good, which is positive. Question number 1. A leisure club offers a choice of one of 3 activities to its 150 members on a Tuesday evening. The manager believes that there may be an association between the choice of activity and the age of the member, and collected the following data, and the data is shown in the table. For part A, we have to write down suitable hypotheses for a test of the manager's belief. Well, for part A, our null hypothesis, there is no association between age and activity. For our alternative hypothesis, there is an association between age and activity. For part B, the manager calculated expected frequencies to use in the test. We have to calculate the expected frequency of members aged 60 or over who choose snooker used by the manager. Okay. So first of all, for this question, the expected frequency, that's given by the row total times by the column total all over the grand total. So let's actually work out the row and column totals. 9 plus 3 plus 3, that would be 15. 10 plus 10 plus 14, that would be 34. 16 plus 15 plus 5, that would be 36. 15 plus 13 plus 11, that would be 39. 4 plus 19 plus 3, that would be 26. For the column totals, 9 plus 10 plus 16 plus 15 plus 4, that would be 54. 3 plus 10 plus 15 plus 13 plus 19, you'd find that to be 60. 3 plus 14 plus 5 plus 11 plus 3, that would be 36. Of course, for the grand total, that's 150. Okay, so we're looking at, for part B of the question, over the age of 60, those who choose snooker, so the expected frequency, that would be 26 times by 36 all over 150. So we have our row total, 26, times our column total, 36, and we divide this by 150. Okay, and if we work this value out, so we have 26 times by 36, dividing this by 150, we end up with 6.24. Okay, now for part C, we have to explain why there are 6 degrees of freedom used in this test. Well, what we can do first of all is work out all the expected frequencies. Okay, so once we do that, if we see that any expected frequencies are less than 5, we'd have to combine the cells together. So here we just work this to be 6.24. Okay, and let's work out the rest of them. So here we have 54 over 150 multiplied by, and what we have to do here then is multiply by 15 first of all. You'd find that to be 5.4. Next we have this multiplied by 34, we end up with 12.24. So we have 12.24, and then here we have 36. So we end up with 12.96. Next, we multiply by 39. We'd find this to be 14.04. And then we have this multiplied by 26. You'd find this to be 9.36. Okay. Next we have here we have 60 over 150, and then we multiply this by 15. We end up with 6, and then we have this multiplied by 34. We end up with 13.6. Next we have this multiplied by 36, which is 14.4, and then we multiply by 39. We end up with 15.6, and then we have this multiplied by 26. We end up with 10.4. Okay, so we end up with 10.4. And then for these last ones, we have 36 over 150 times 26, that's a 6.24 we just worked out. And then we have this multiplied by 15. We end up with 3.6. And then if we multiply by 34, we end up with 8.16. And then if we multiply through by 36, we end up with 8.64. And then if we multiply by 39, we end up with 9.36. Okay, so those are our expected values. Now, what does this mean? Well, you'll notice over here, for the age being less than 20 and snooker, we have a value of 3.6, and this is less than 5, so we'd have to combine the rows. So let's just quickly write that down. So for A being less than 20 and snooker, this 3.6, this expected frequency is less than 5, so we'd have to combine the rows. So when we do that, we come out with the following table. So we've got this table here. We can combine these two rows here, anything less than 40. So let's just add together the observed values. So 9 plus 10, that's 19. And then for balls, 3 plus 10, that's 13. And then for snooker, 3 plus 14, that's 17. And then for the rest of the values, those remain the same. So we have 16, 15, 5, 15, 13, 11, 4, 19, and 3. So when we come to talk about the degrees of freedom of this table, we can now see that the table is a 4 times by 3 table, and therefore the degrees of freedom, that would be 4 minus 1 lots of 3 minus 1, which is 6. Okay, now for part D, we're told that the test statistic used to test the manager's belief is 19.583. You can find that out by working out the observed minus the expected, then square that value and then divide by the expected, and then add them all up together. But we're told so far that the test statistic is 19.583. Okay, and what we have to do is using a 5% level of significance, complete the test of the manager's belief. Well, we've got 6 degrees of freedom, and what we can now do is find out the critical value, and we're testing at the 5% level of significance. So we've got 6 degrees of freedom at the 5% level of significance, and if we go to the formula book, we can find out what this critical value is. So just go to this table over here. We have 6 degrees of freedom, 5% level of significance. You'd find the critical value to be 12.592. So we have 12.592. So drawing a quick diagram to illustrate this, we've got our critical value of 12.592. Here is where we reject H0, and here is where we accept H0. And we've just found the value to be 19.583. We were told that in the question. So what we have over here then is the 19.583. So we're in the region where we reject H0. So we have the following conclusion to make. So we reject H0 clearly, and therefore there's evidence to support the manager's belief. Question 1. Examiner report wise, nearly all the candidates knew the hypotheses were about association or independence and mentioned the context, but a surprising number gave H0 and H1 the wrong way around. So it's good that you have to give the context, so that's over here, but you have to make sure that you get H0 and H1 the right way around. Okay, so we've got null and alternate hypotheses. Part B, that was answered quite well to find out the expected value, and the critical value in part D was usually quoted correctly, with those 2 marks being scored by the vast majority of candidates. Okay, so that's that mentioned. However, for part C, where we had to explain why there's 6 degrees of freedom, this one gave a bit of trouble. The examiners were looking for candidates to realise that some of the rows would need to be basically combined because some expected frequencies were less than 5. So I think actually working out all the expected frequencies and noticing this is less than 5 would have made life a bit easier for yourself. Some calculated all the expected frequencies, but their calculation part B should have been steered them to the top right hand cell, which had an expected frequency of 3.6. I mean, that actually does make sense, because over here for a value of 26 we come out with this value over here. So for something like 15, of course we're going to come up with a much smaller value. But just to be on the safe side, I don't see anything wrong with doing this. So what else was mentioned? And therefore meant that some amalgamation was required. Those with the small expected frequencies and the ensuing 4 times by 3 table will lead to 6 degrees of freedom, so that's when you combine. And some confused rows and columns, or just mentioned vaguely combining cells. A common error was to think the joining of cells was required because the observed frequencies being less than 5, and this sometimes led to combining snooker and balls, or the first and last rows. So essentially just had to combine them two, and others simply thought that the 6 came from the calculation of 8 minus 2. I don't know where that 8 came from, presumably confusing with the calculations required for a goodness of fit test. But in the final part of the answer, so what is the final part of the answer? Only a small minority did not know how to use the tables and gave the value of 1.635, and those who had their hypothesis the correct way around in part A were usually able to give an appropriate conclusion, either in terms of there being evidence of association between age and choice of activity, or more simply stating that there was evidence to support the manager's belief. So when you give your conclusion, make sure you give it in terms of context of your hypotheses over here. Question number 2. A spinner used for a game is designed to give scores with the following probabilities. So we've got the score and then the probability. The score can either be 1, 2, 3, 4 or 6, and the spinner is spun 80 times and the results are as follows. So we have to test at the 10% level of significance whether or not the spinner is giving scores as it is designed to do. Show your working and state your hypotheses clearly. Well, we've got our hypotheses. The null hypothesis, the spinner is working as designed. The alternative hypothesis, the spinner is not working as designed. Now, what we can first of all do is find out the degrees of freedom. The degrees of freedom would be, well, here we have 5 columns, 2 rows, so we have 2 minus 1 lots of 5 minus 1, which is 4. And we're testing at the 10% level of significance. So first of all, we can find out our critical value. So we've got 4 degrees of freedom. We're testing at the 10% level of significance. So if we grab a different color, we have 4 degrees of freedom. The 10% level of significance, that would be 7.779. Okay, so we have 7.779 as our critical value. And now we need to find out our test statistic. And to do this, we can construct a table. So we have score. The score we'll call X. We've got the probability that the random variable X equals Xi. We've got the observed values, the expected values, and then we've got the observed minus the expected all squared all over the expected squared. So we've got our scores 1. We've got scores 1, 2, 3, 4, 1, 2, 3, 4 and 6. And we've got those probabilities. Here we have 3/10. Here we have 1/10. Here we have 2/5. Sorry, no we don't. We have 1/10. 1/10 again. 2/5 and 1/10. Okay, and our observed values, we have 15, 4, 12, 41 and 8, and we can find out the expected values by multiplying these probabilities by 80. 3/10 times by 80, that would be 24. 1/10 times by 80, that would be 8. So we have 8 here, here and here. And 2/5 times by 80, that would be 32. So if we work out the observed minus the expected all squared over the expected, well, working this out, we have here 15 minus 24 all squared divided by the 24, which is 27 over 8. And then 4 take away 8 all squared over 8, that would be 2. So we have 2 here, 2 here. 8 minus 8, that's 0. 41 take away 32 squared, and then divide by 32. We end up with 32. 81 over 32. Okay, so to find out our test statistic, that's equal to the sum of the observed minus the expected all squared over the expected. So we have 27 over 8 plus 2 plus 2 plus 81 over 32 plus 0. I'm working this out. So 27 divided by 8 plus 4 plus 81 over 32, we end up with a value of 9.90625. Okay, so drawing a diagram to illustrate these, so we've got this diagram here. We've got our critical value, that would be 7.779. Here is where we reject H0. Here is where we accept H0. We have our value, test statistic, which is 9.90625, and therefore clearly we're in the region where we reject H0, so we can make the following conclusion. So we can reject H0 clearly, and therefore there's evidence that the spinner is not operating as designed. Question 2, this was concerning, by the looks of it, well, this was answered quite well. Some lost marks for the hypotheses again. Statements such as observed frequencies match the expected frequencies, or a uniform distribution is a suitable method were given, rather than to comment about the spinner's design, such as the spinner is given probabilities as it is designed to do. The expected frequencies were usually found correctly, but a number of candidates lost marks for incorrectly combining the scores for 1 and 2 because the observed frequency for a score of 2 was less than 5. So essentially what you have to do over here is you're not looking at the observed frequency, you're looking at the expected frequencies, and all the expected frequencies are greater than 5. Candidates need to understand that the amalgamation of cells is only required when the expected frequency falls below 5, so that's what I just said. The calculations and selection of the critical values, the value were usually correct, and most realized that the test suggested the spinner was not working as designed because you reject H0. And I think if you draw a quick diagram, that helps to visualize that. Question number 3. Andrea's secretary makes random errors in his work at an average rate of 1.7 errors every 100 words. He should be fired for that. For part A, we have to find the probability that the secretary makes fewer than 2 errors in the next 100 word piece of work. Okay. So clearly we can model this within Poisson distribution. So if we let x be the number of errors in the 100 word piece, so let's just write this down for part A. If we let the random variable x be the number of errors in 100 word piece, then we can model this with a Poisson distribution with parameter 1.7. And in this question, we're looking at the probability that x is less than 2. So this is the same as the probability that x is less than or equal to 1. And if we work this value out, so for this we need to go to the distribution section. We have a Poisson cumulative, click variable, we have 1 here and 1.7 here, so we end up with 0.493, etc. For part B, Andrea asks the secretary to produce a 250-word article for a magazine. We have to find the probability that there are exactly 5 errors in this article. Well, for part B, if we let R be the number of errors in the 500-word piece, then first of all we need to calculate our new rate. We have 1.7 times by 250 over 100. The reason for this time, instead of looking at the 100 words, we're looking at 250 words. So if we work this out, 1.7 times by 2.5, you'd find this to be 4.25. And therefore, we can see that we can model R with a Poisson distribution with parameter 4.25. And therefore, if we solve for the probability that R equals 5, we can work this out quite easily. So back to the distribution section, we have a Poisson PD, x is equal to 5, lambda that's equal to 4.25, we end up with 0.164, etc. Okay, so now for part C of the question, a bit more difficult this time. Andrea offers the secretary a choice of one of 2 bonus schemes based on a random sample of 40 pieces of work, each consisting of 100 words. In scheme A, the secretary will receive the bonus if more than 10 of the 40 pieces of work contain no errors, and in scheme B, the bonus is awarded if the total number of errors in all 40 pieces of work is fewer than 56. So first of all, we can find out what the probability of containing no errors will be, okay, per 100 words. And with that, we can create a binomial distribution because we have a sample of 40. And we're looking at then with scheme A, from this sample of 40, that we have more than 10. So for part C of the question, first of all, the probability that x is equal to 10, let's work this out. Remember, x is the random variable of the number of errors in 100 word piece. We have parameter 1.7. So if we go to our distribution section, we have Poisson PD, x is equal to 0, lambda that's equal to 1.7. So we end up with 0.182, etc. Okay, and with scheme A, we can model that with a binomial distribution. We have 40 in our sample. Our probability, we just worked that to be 1.82, etc. We're looking at here the probability that we have A being greater than 10, which is the same as 1 minus the probability that A is less than or equal to 10. So we have 1 minus, well, if I store this into A, binomial CD, so x is equal to 10, n is equal to 40, the probability that's equal to A. So we have 1 minus the 0.9004, etc. So we have 1 minus this, which is 0.0995, etc. Okay, so let's just summarize what we've done over here. Sorry, we have no errors. So what we've done over here is we found the probability that we have no errors. Okay, and we created this binomial distribution based on the fact that we have for scheme A 40 pieces of work that contains no errors. Obviously, with our sample of 40, picking each of those 40 will be independent of each other, and then we're looking at more than 10. So here we're looking at the probability that A is greater than 10. Okay, so that's with scheme A. With scheme B, however, we can model this with a Poisson distribution. Now, if you look over here back to the question, that we're looking over here that the total number of errors in all 40 pieces of work is fewer than 56. So for each piece, remember each piece contains 100 words and the average rate of error for each piece is 1.7. So for 40 of them, we have 40 times by 1.7. Okay, so let's just get a different color to highlight this. So here we multiply by 1.7 by 40 because we're looking at the total number of errors in all 40 pieces. Remember, in one piece the error was 1.7. So what we have here then is B, which has Poisson distribution with parameter 40 times by 1.7, that's 68. So we're looking at here the probability that B is less than 56. We were told this in the question as well, so this bit over here is what we're looking at here, fewer than 56. And what this is the same as, this here is the same as the probability that B is less than or equal to 55. So working this out, so back here to the distribution section, we have a Poisson CD variable 55 here and 68 here, and we end up with 0.0611, etc. So which one should we choose? Well, the probability of bonus is clearly higher for A because this value is greater than this value. So therefore we should choose scheme A because the probability of bonus is greater. Okay, so that's that done. Now for part D of the question, following the bonus scheme, Andrea randomly selects a single 500 word piece of work from the secretary to test if there is any evidence that the secretary's rate of errors has decreased. Stating your hypotheses clearly and using the 5% level of significance, we have to find the critical region for the test. So what we're looking at over here is to see if the rate of errors has decreased. And what we mean by that is, when we talk about to see if the rate of errors has decreased, well, currently we know the rate of error is 1.7. Okay, so we're testing whether this has increased or decreased. So for H0, we're testing if lambda equals 1.7. That's our null hypothesis, and for our alternative hypothesis, we're looking if this has decreased. So we're looking at lambda being less than 1.7. So that's what we mean over here. Now, our new mean, which we need to look at, this time he selects a 500 word piece. So we have to work out a new mean for a new Poisson distribution. We'll call this mu, and that will equal 1.7 times by 500 over 100, which is 8.5. Okay? So this comes from the fact that he's looking at a 500 word piece of work from the secretary. Okay? And what we can do is, if we let the random variable e, so let's just write this down. So if we let the random variable e be the number of errors in a piece of work, then we can model this with a Poisson distribution with parameter 8.5. Okay, and what we're looking at over here is for some critical region. So drawing a diagram hopefully will help to visualize what we're on about. So what we have over here then is a lower tail test, because we're looking at if the mean has decreased. We've got a mean of 8.5, and we're looking out for some critical value. We'll call this EL for E lower, for the lower tail test. Okay, so here is where we reject H0, and here obviously is where we accept H0. And hopefully you can see that we reject H0 if the probability that E is less than or equal to this lower value is less than or equal to 5%. Okay, and the reason we're looking at this 5%, quite obvious. We're having a 5% level of significance. So to find this value, we can use our the tables. So using tables, what you can hopefully see is, well, if we actually take a look somewhere in the tables, well, we have a Poisson distribution. We have 8.5, so let's just get a different color. So we have 8.5, and if you look down here, it's either going to be in between this value or this value, and this value is clearly less than 5%, so that corresponds to x equaling 3. So what we can see then is EL, that's equal to 3. Okay, and therefore we reject H0 if P, the probability that E is less than or equal to 3. Well, we reject H0 as the probability of E being less than or equal to 3 is equal to the 0.03 or 1, which we've just seen from the tables. and therefore the critical region, that would be E being less than or equal to 3. Okay, so hopefully that makes sense. Question 3. Only a few candidates did not realise the significance of the terms random and average rate and used binomial rather than Poisson models throughout the question, but for most candidates this question provided a good source of marks. In part A, the most frequent error was the misinterpretation of the phrase fewer than 2, with many simplifying the probability of less than or being equal to 2. So fewer than 2 does not mean less than or equal to 2. So that's talking about this over here. So responses to part B were often better and most found the new Poisson distribution and used it correctly. Part C was the most challenging part of the question, with many unable to work out the probability connected with scheme A. So what did we have to do for that? So that was this part over here. So let's have a read why that was. Most realised there was something to do with a Poisson with 1.7 model, but far fewer realizing that finding the probability that x equals 0, where x is has a Poisson distribution of 1.7, was giving them a parameter of the binomial model, and I'll discuss that over here, and that's highlighted. Those who realize this often fail to use sufficient accuracy to achieve their final probability correct to 3 significant figures, and why having a binomial distribution with parameters 40 and 0.183 were commonly used. The next problem was interpreting more than 10 correctly, and many failed to use this as 1 minus the probability that y is less than or equal to 10. So that's on about this line over here. There was often more success with the probability associated with scheme B, and those who had correct probabilities were usually able to correctly recognize scheme A. There were many correct answers to part D, with hypotheses usually given in terms of something missing here. But the common errors were to leave the final answer as the probability of being less than or equal to 3, rather than the expected being less than or equal to 3, or confusing a critical region with a critical value and having a final error of E equals 3. So because it says region, we have to give a inequality. Question number 4. The discrete random variable x has probability distribution shown here, where q and r are probabilities. For part A, we have to write down in terms of q the probability that x is less than or equal to 0. Quite straightforward. The probability that x is less than or equal to 0, well, if you look at your table, less than or equal to 0, well, we can either have the probability that x is equal to minus 3, or we can, and we have the probability that x is equal to minus 1. So working that out, we end up with q plus 7 over 30. Okay, that's part A done. Part B, we have to show that the expected value of x squared is equal to 7 over 15 plus 13q plus 16r. Okay. Well, for this, we'd have to construct a new table. So we've got x squared, and the probability that x is equal to x. Okay, so we've got minus 3, minus 1, 1, 2, and 4. So here x squared, that would be 9, 1, 1, 2, 4, and 16. And these probabilities haven't changed. We have q 7 over 30, 7 over 30, q, and r. So the expected value of x squared, that's equal to the sum of the x squared times by the probability that x is equal to x. So we have 9 lots of q plus 1 lots of 7 over 30 plus 1 lots of 7 over 30 plus 4 lots of q plus 16 lots of r. And if we tidy all this up, well, here we have 7 over 30 times 2, which is 7 over 15. And then we have here 9q plus 4q, which is 13q. And then we have, in terms of r's, just a 16r as well. Okay, so that's what we wanted to show. And now for part C, given that the expected value of x cubed is equal to the expected value of x squared plus 6, the expected value of 6x, we have to find the value of q and the value of r. Okay, so, well, first of all, you can hopefully recognize that probability adds up to 1. So the sum of probabilities is equal to 1. So with this, we have the q plus the 7 over 30 plus another 7 over 30 plus q plus r. This is equal to 1. So we can hopefully see that we have the equation 2q plus r equals 16 over 30. Okay, so here we end up with 14 over 30, and 1 minus 14 over 30 is 16 over 30. Now, what we can do over here, well, here we've got something involving an x squared, and what we can also do is work out the expected value of x with it. So the expected value of x, that's equal to the sum of the x's times by the probability that x is equal to x. So we have to multiply this first row with this probability row. So we have minus 3 times by q plus minus 1 times by 7 over 30 plus 1 lots of 7 over 30 plus 2 lots of q plus 4 lots of r. So we end up with here 4r minus q. Okay, and what we can also do is, if we construct this table again, this time with that we can work out the expected value of x cubed. So we've got x cubed, and then the probability that x is equal to x. So with this, well, we have x values of minus 3, minus 1, 1, 2, 4. X cubed, well, here we'll have minus 27, minus 1, 1, 8, and 64. The probabilities haven't changed, so we have q 7 over 30, 7 over 30, q, and r. So for the expected value of x cubed, that's equal to the sum of the x cubes times by the probability that x is equal to x. So we have minus 27 times by q plus minus 1 times by 7 over 30 plus 1 lots of 7 over 30 plus 8 lots of q plus 64 times by r. So we end up with 64r minus 19q. Okay, and we were told that this value over here, well, actually let's just label our equations. Call this equation 1, call this equation 2, call this equation 3, we'll call this equation 4, and call this equation 5. We can hopefully see that, well, if you look over here, we've got expected value of x squared plus 6, plus the expected value of 6x. And with that, let's just write this down. We've got this plus this over here. Okay, and we can rewrite this as the expected value of x squared plus 6 lots of the expected value of x. So this thing over here we've just worked out over here, that was 7/15 plus 13q plus 16r. So this thing corresponds to this thing, which is what we worked out over here. Okay, and then we've got 6 lots of the expected value of x, so we add on 6 lots of what we had over here, 4r minus q. So we have 4r minus q, and this thing over here is what we had over here. Okay, so this is the expected value of x. So if we tidy all this up, well, we have 7/15, and then we have 13q plus 6 lots of minus q, that would be 7q, and then 16r plus 24r, that would be 40r. We'll call this equation number 6. Okay, and we know that this entire thing over here is the same, well, this thing over here we were told is the same as this thing over here. So this over here is equal to what we had over here, and that's this. So what we can therefore see then is, if we set 5 equal to 6, we have 64r minus 19q equals 7/15, so that is this bit over here, plus 7q plus 40r. And if we tidy all this up, take everything over to one side, we have 24r, so that's 64r take away 4r, 40r, and then we have minus 26q, and this is equal to 7/15. Okay, we'll call this equation 7, and we've got this equation number 3 over here. So if we solve equation number 3 and equation number 7 simultaneously, what you can hopefully see over here then is q and r we can find. So for this first equation, we have a simultaneous equation with degree 2, so we have 2, 1, 16/30, and for the next one we have minus 26, 24 and 7/15. So we see that q is equal to 1/6 and r is equal to 1/5. Okay, so that's that done. So what can we say from here? Well, we've got x and the probability that x is equal to x. So we've got minus 3, minus 1, 1, 2 and 4. And knowing the values of q and r, we have 1/6 here, 7/30, 7/30, 7/30, 1 over 6, and 1 over 5. Okay, so that's that done. And now for part D, hence find the probability that x cubed is greater than x squared plus 6x. Okay, so part D of the question. Well, if we look at this x cubed being greater than x squared plus 6x, we can rewrite this as x cubed minus x squared minus 6x being greater than 0. So we have x lots of x squared minus x minus 6 being greater than 0. So therefore we have x lots of x minus 3 lots of x plus 2 being greater than 0. So our critical values, we have x equals 0, minus 2, and 3. So if we solve this inequality, so let's quickly sketch it out. So if we sketch out a quick graph, graph looks something like this. It crosses at 3, 0, and minus 2, and it's greater than 0 here and here. So therefore we can see that we have minus 2 being less than or equal to x being less than or equal to 0, or we have x being greater than 3. So in other words, the probability that x cubed being greater than x squared plus 6x, well, in between minus 2 and 0, if you go back to this table here, in between minus 2 and 0, well, that would be this minus 1 from that table. So we're looking at the probability that x is equal to minus 1. And then x being greater than 3, well, x being greater than 3, that just leaves x being equal to 4. So adding these together, we have 7 over 30 plus 1 over 5, which is 13 over 30. Question 4 of the question, parts A and B were answered quite well, but a few candidates miscopied their 16R as 6R and proceeded to use this incorrect value in part C. For part C of the question, where we have to find the value of Q and R, many made a start by finding the expected value of x and then 6 times by the expected value of x, and then this bit over here they found from this bit. Many managed to find an expression for the expected value of x cubed, though sometimes there were sign errors on the negative terms. Finding the probability, finding a second equation in Q and R seemed to evade a few, but most used the sum of probabilities to form a second equation and were able to solve the two equations, which, if no previous errors had been made, gave the correct answer. For part D, where we had to find this probability, there were a couple of few blank responses and a few who tried comparing expected values and then gave up, but a good number made a start on part D, and quite a few of them, with the help of the A1, with the final A1 follow-through mark, achieved all 4 marks. Some stated by rearranging the inequality and factorizing the cubic, but often they were stopped here, seemingly unable to draw a simple sketch or solve this cubic inequality. I don't think that was actually quite difficult. It's something that you can even do it on your calculator as well, solving a cubic inequality, so it's not a hard thing to do. And that's of course once you rearrange correctly, like you've done over here. So after that, the most common approach though was to form a table with the 10 values for x cubed and x squared plus 6x, which I didn't do, and comparing these values to identify x equals minus 1 and 4 as the required cases, and then write down the appropriate probability. I didn't do that, but I think my way is sufficiently fine as well.